Hello everyone, welcome to my video. I'm Venkata Subramaniam, Assistant Professor, Civil Department. The subject code is OEE 351, Renewable Energy System, Regulation 2001. Now we are going to see about Unit 2, Part 2, the continuation of Part 1. In this Unit 2, Part 2 video, we are going to see about solar thermal energy conversion, how this solar energy is converted to thermal and how it is utilized, which is we are going to see about in this video. Okay, introduction to solar thermal conversion concept. The converting solar radiation to the thermal energy, which already we are told, to the heat energy using a collector device. The process is absorption of solar radiation first. Second one is transfer of heat to the working fluid, water, air, or oil, and utilization of heat for domestic or industrial applications. There are two classifications. One is non-concentrating, another one is concentrating. In the non-concentrating, we are using FPC, flat plate collectors. Concentrating type, we are using parabolic through dish and power tower. Flat plate collectors, the most common collector for a low temperature application, less than 100 degrees Celsius. The main components are glazing, glass cover to reduce the convection and radiation losses, and greenhouse effects. And absorber plate usually having copper or aluminum coated in a black to maximum absorption. And insulation, backside of the insulator to provide the heat loss without escaping that heat energy which is absorbed. And flow tubes, channels of the heat transfer fluid. These are the heat transfer fluid which is transferred by the flow tubes. The working principle of FPC, solar radiation passes through the transparent glass, that is glass, and absorber plate gets heated and transfer heat to the fluid tubes. Here, greenhouse effect is happening. So, the glass allows short wave of solar radiation to enter the traps. It's a long wave thermal radiation from the plate, increasing efficiency. So, here we are using greenhouse effect to absorb the radiation from the heat energy. Now we are going to see about concentrating collectors focusing type. The purpose to achieve high temperature, that is greater than 100 degrees Celsius, by concentrating sunlight from the large area onto a small receiver. That is, from the large area we will concentrate that to the one particular point. This can be calculated using concentration ratio formula, CR equal to area of aperture size by area of receiver size. That is, aperture means it will be all mirror concentrating to the one area, that is called the aperture area, which is divided by the area of receiver. Types: point focus and line focus. There are two types. One is point focus, example parabolic dish. Line focus is a parabolic trough. And next we are going to see about types of concentrating collectors. Use a high temperature application power generation, parabolic rod, and solar power tower, and parabolic dish. Focusing light on a receiver pipe, that is parabolic trough, and solar power tower, which is a field of mirrors, which can be said as heliostates, focusing a light on a central tower. There is a tower which is connected, that can be concentrated to the central tower. And another is parabolic dish, this focus point system, Stirling engines, a point focus system. That is, this is a parabolic dish. We can control the mirrors to the high temperature for Stirling engines. Next, performance analysis engine, energy balance. Performance analysis energy balance is we have the heat energy, but we will also lose the heat energy because of the some loss uh, on the device. This can be calculated using the performance of the collector governed by energy balance equation, which is given by QU equal to AC into IT into tau alpha minus UL TP minus TA. Here QU is a useful heat energy gained by the absorber and collector area, that is AC, and incident solar radiation, which is IT. And tau alpha is a transmissivity and absorptivity product. Absorptivity and transmissivity product of these two. And UL is a overall heat loss coefficient. And TP minus T is a temperature difference, plate and ambient. Now we see the collector efficiency eta. Definition of ratio of useful gain to the incident solar. That is the efficiency, right? How much input solar energy given and the ratio useful energy we gained. This simply we can divide the QU by AC into IT. The AC is a value which is solar energy given and the IT, which is equal to FR into tau alpha minus UL into TI minus TA all divided by IT. The key factor here, FR, the collector heat removal factor, is called collector heat removal factor, which is represents effectiveness of the heat transfer to the fluid. Factors affecting the performance. Since we are receiving the heat energy, but some factors is affecting to gain the 100% heat. This is selective coatings. First thing, selective coating and number of glazing covers and tilt angle and dust and soiling. Selective coating increases the absorption while reducing thermal emittance. Number of glazing covers, if it is more covers, reduce the heat loss, but also reduce the incoming light, right? So if more cover, heat loss reduced, but reducing incoming light will be low. And tilt angle, ideally equal to the latitude of the location. If tilt angle is different, if it is changed, then we'll get the loss in energy. Then dust and soiling can significantly drop efficiency of the not clean. If it is dirty, the solar panel or module is dirty, then you will get the efficiency also very low. So finally we came to conclusion, the part 2, unit 2 part 2. Flat plate. First thing is flat plate we have seen, which is water heating and space heating and solar drying. These are the applications of flat plate. And concentrating, you can say that solar thermal power plants, CSP, and industrial process heating and melting metals. And future trend, integration of thermal energy to provide power even when sun isn't shining. This is our future trend. This can be achieved by thermal energy storage devices. We'll see the other topics in the next video. Thank you.